Hi, my name is Julieta Diaz and I'm a data scientist at TIBCO. Welcome to this Team Studio enablement video. In this video, I will cover how to use Team Studio to solve a classification problem. We are going to use the Elastic-Net Logistic Regression and the EBase Operators, among others. We are starting from the Workfiles tab in a workspace I have previously created, and we will click on the classification workflow to get to the workflow canvas you can see here. Let's say we want to try to do some classification on a classic dataset, the iris dataset. This dataset includes 3 iris species with 500 samples each, and it is composed of 5 columns. 4 columns of measures on the sepal and pearl, and the column containing the labels, setosa, versicolor, and virginica. In this particular dataset, we want to create a predictive model that will tell us the species of the iris plants based on some properties of the flowers. I have already split the data into a train and test set, so we are ready to drop into the canvas our classification models. You can find all the model operators that are available to you by selecting Model from the Operator drop-down, and we can see the different options that we have. In this case, I'm going to drag in the Elastic-Net Logistic Regression and the EBase Operators, both of them for classification tasks. I want to see which of these two models will give me a better prediction, closer to the actual values that we have. So if we connect our training set to the models, we don't have to configure them. Let's start with the logistic regression. The Elastic-Net Logistic Regression is a logistic regression model with an Elastic-Net regularization. It is an extension of logistic regression that adds regularization penalties to the loss function during the training. This method combines two popular penalties, the L1 and L2 penalty functions of the lasso and ridge methods. The benefit is that ElasticNet allows a balance of both penalties, which can result in a better performance than a model with either one or the other penalty on some problems. The first thing we need to define is the dependent column. This is the target column, the one that we are trying to predict. In our case, it is species. Now, the column selection here is a way to be able to filter out certain features. You might know about your data that some information might not be relevant to you, and therefore you don't necessarily want to throw it into creating this model. It might just be noise. It might be useless, it might not have any significance on your model, or you might already know anything about this. So here you have options to select different columns. For our purposes, I'm just going to use all the available columns as predictors. We can also specify whether we want to normalize the numerical features using a C transformation and the metric for evaluating the performance of the model during the cross-validation training. The default function is the accuracy for binary classification and the F measure for multi-class classification. The next parameter that we can configure is the maximum number of iterations for each grid of parameters. That's how many times whatever model you will be using will run. It's the steps of modeling. There are also more details available. So, for example, you can specify the convergence tolerance, the parameter grid for lasso logistic regression, the number of cross-validation faults, etc. If you ever need more information, you can just go to this question mark here at the right, and that takes you straight to the documentation to tell you more about how this operator works in Team Studio. Now we will configure the EBase operator. This algorithm is based on applying Bayes' theorem with the naive assumption of conditional independence between every pair of features given the value of the class variable. Now, if we look at the edit operator properties of this operator, you will see again that the dependent column has to be specified. The columns must be selected as well. We are going to use all the available columns so that we can compare the two models with exactly the same features as input. There are two more parameters that we can configure. The model type. There are 4 types of naive-Bayes models under Teams Studio. The multinomial, which is used for discrete counts. The complement, this is an adaptation of the multinomial that is particularly suited for imbalanced datasets. The Bernoulli, this is similar to the multinomial, but the predictors are Boolean variables. And finally, the Gaussian, which assumes that the features follow a normal distribution. We are going to select Gaussian here. And another parameter that you can also specify is the additive smoothing parameter. This value must be non-negative and the default value is 1. Again, if you want to look at the documentation to better understand the parameters, you just click on the question mark. So we have 2 classifiers here, but how do we compare and see which one is doing better with our dataset? Essentially, you will look at the Predict tab here on the left-hand side, which will pull up the different types of evaluators that you could use. A good one for classification is the confusion matrix. That's especially important in places where maybe a false positive might be what you are trying to mitigate. Again, it depends on your circumstances and what you are trying to do. But I'm going to drop into the canvas the confusion matrix and the goodness of fit operators. Now, the way to configure these predictive parts of the classifier is directly drawing in the test set to them. The testing set, the confusion matrix, and the goodness of fit understand that the logistic regression, when it is connected to each of these different predictor variables, will then use the test set to evaluate and give us the results back. So let's do the same for the naive Bayes operator. We can run this, and once the flow has finished running, we can see some interesting information about our different classifiers. For example, in the logistic regression output, we have several sorts of outputs, but the most important ones are the coefficients, which displays the coefficients for each value to predict and the reference class. And also the training summary, which shows a table with a row per each tested combination of hyperparameters in our grid, along with the metrics and the best model. If you look at the output of the goodness of fit operator, we can see that the goodness of fit metrics for each class was computed, including accuracy, error, recall, precision, and the F-score. We can notice that the logistic regression is performing better than the naive Bayes model. We also have the confusion metrics here for the different types of classifiers. The accuracy for the naive Bayes was 0.94, while for the logistic regression was 1. So based on this, we might say that the logistic regression is the better model and therefore the one to be focusing on for our predictive purposes. Thank you for watching.